Newton's third law is really interesting. So once you get past Newton's first law and then move over to Newton's second law, when you start talking about the net force and objects accelerating, you're going to move over into Newton's third law. And what it states is the following. So you have that for every action, force that you exert, okay, or something exerts, there is an equal, and it's simultaneous, and it is opposite in direction, okay, and that is called the reaction force. So it is very nicely captured by a simple equation. So you have for every action that you take, because a force is a vector, so there is a direction here, and we're going to assume that the positive direction is in the direction of the action. And therefore you have an equal, and it's simultaneous, force of reaction, and it is in the opposite direction. So that's the negative. So the negative just simply means it's in the opposite direction. So if you were thinking about an object, so if here is an object and you have an action force, okay, here is your reaction force that you have, and they're both equal. They're just in opposite directions. Now, where does this come into play? And for students, it's actually hard to understand. And sometimes if you're doing physics, even for a little while, it's a difficult concept to grasp. You know, every action has a reaction. You maybe have heard of this, never mind in terms of forces, but you even have this in human nature. If there's certain things that happen, you know, then there's reactions, especially if you're thinking about maybe emotions. But let's put that on the side and let's come back to physics, something that we can actually measure and observe, okay, through the scientific method. So I'm going to give you a few examples here, and I'm going to try to illustrate how this concept actually works. Like, what does that mean for every action that there is a reaction? And you have to think about of intuitively what is happening in terms of no motion or what is causing the motion. So first of all, one of the easier things to do and to think about is, you know, I am currently actually sitting. So now if I was thinking about sitting and I was trying to draw a free body diagram for myself, so let's say this is me, I'm a box, and I know that gravity is definitely, okay, trying to pull me down. So it's almost like this is some kind of an action force from gravity. Now, the chair that I'm sitting on, so you can imagine, I'm going to just put a chair right here, okay? I'll just put it as a line, but you can see that, you know, here's my butt and it's sitting on the chair. So there is an action force actually from me because I have a mass, okay? And then the pull of gravity is going to be pushing on this particular chair. So you have a action force that is now pushing in that direction. So that is, and I'll put action, maybe I'll just write A so I don't have to write out the full word. And it is down. Now, but I'm not falling through the chair, right? So I am pushing on the chair, okay, because I have a mass, and then there's gravity which is trying to pull me down through that chair. Okay, but I'm not breaking the actual bonds of that chair. And what happens is at that particular instant, and I'm going to erase myself here, you will find that there is exactly the same type of force which is preventing me from falling through the chair. So it is equal to this, but it is opposite in direction. So it will be in that direction, which is upwards, and that would have been my force of my reaction. And notice that here that the force of action that I'm putting is equal to the force of reaction that I have. Now it is in the opposite direction. So if I'm assuming that positive is down, so if positive is down, therefore I would need this negative symbol here to represent my force of reaction properly. And that's why you'll see that negative there. In magnitude wise, if you're only thinking about magnitude, then that magnitudes there will be just simply the same. If you want to ensure that it's vectors, you do need that negative just to let the actual reader know that it is in the opposite direction of whatever you choose, okay, the positive be for that action. So that's sitting, and that is any action that you will take, right? And where there is really no motion, okay, that you have, no acceleration which is caused. you can literally push on the wall, right? As you're pushing on the wall, that could be the action on the wall. But the wall itself, it's made out of atoms and there's bonds within there. Well, the wall doesn't want to break down. So it's going to provide a reaction force on you. And, as you're pushing on the wall, you will feel that there is actually a push on your hands back, right? So this is what you do. And that wall is going to be, pushing back. If you're doing push-ups, for example, and you're on the ground, right? Well, it's called a push-up, right? So you are actually exerting the push on the ground, and then the ground is pushing you back, and then the goal is ultimately to try to lift yourself up. So you have an action force and a reaction force. Now, how does walking now work? So if you're thinking about walking in here, so what do we do, okay, if we want to propel ourselves forward? And this is anything to do. The same thing happens actually with swimming, okay, and we can definitely talk about a rocket taking off. So this sitting concept was actually stationary, right? We're not falling through. But all of the other ones that I'm listing here, I want to show you that it's the actual reaction force that is allowing us to move ourselves, okay, in whatever direction we have. So when you're walking, okay, and let's imagine, here's, your foot that you have. Now, I know that your foot is not necessarily a rectangular shape, but what do we do, okay, when we push, right? So typically, push off and, our foot might kind of look like this, right? So this is our, our foot, okay, right here, maybe these are our toes, okay, right there. What do we do? Well, what we're actually doing is we're trying to, okay, push, okay, against the ground. Now, we're not necessarily not vertical. The push is most likely more like this because we're kind of standing upwards. So we're pushing in some way. I mean, ideally, we would want to push in this. This would be much more efficient. But typically, we'll push in some action like this, right? So this particular force, the component which is in the horizontal direction, so this particular component of that push against the ground, what allows us, to move ourselves forward. So yes, there's friction, which is static friction. It's going to keep us stationary, right? We're not going to be sliding on that ground, right? So it's doing that. But then there is a reaction force. So this force is the force of action. And then the ground itself will allow us to move, our actual foot, okay, and us eventually as we're walking through. And this is the reaction force, okay, that we have. And notice it is opposite in the direction to allow us to keep moving forward. So we need that reaction force. So the ground is basically propelling us because it is, okay, going against the action. You do the action of pushing against the ground, and then the ground is actually pushing back against you, okay, and that's the reaction that happens. Now, that is not very intuitive for us to think about, right? Until you start breaking it down and say that, but hold on a second, we are moving. So like, what is causing the movement? Well, movements must be caused by some forces. So this comes back from Newton's second law that we have, and also, of course, from Newton's first law, if there's kind of no movement or stationary movement. So that's what you have to think about. Now, what happens in terms of, let's say, if someone is swimming, okay, and you do have it, okay, you're kind of trying to propel yourself through the water. So what are you doing? Well, you typically will grab, right? You're going to be grabbing it in. So for anybody who's a swimmer, or are you kicking, right? So you're actually trying to accelerate the water in the opposite direction. And here you're pushing against the water backwards, right? So now notice which way. You're not going to be pushing this way, to move yourself that way. What do? You always, right, as you're pulling or as you're walking, right, what you're pushing is in the opposite direction of the way that you want to go. So as you're swimming, you're not going to be pushing this way. You're going to be pushing that way against the water. So that push, that action force now allows the water itself to provide you the reaction force to allow you to go in the direction you want. So when you are propelling yourself, the actions that you exert, walking, swimming, whatever it might be, is in the opposite direction of the direction you want to go, because you want the reaction force. You're relying on Newton's third law to move yourself in that direction. The same thing happens in a rocket. So when you have a rocket, so within that particular rocket, when that rocket is trying to take off, so here is, my little rocket. Let's say that you have, within here, okay, you have a tank, okay, of gas, right? Now gas, this is going to be in liquid form, but it's going to change back into gas form. And if you would zoom in here, so if I'm going to zoom in right into here, right, and I am now referring to this, okay, so what's going to happen that you're going to have now, of course, you have gases that are being pushed out, right? So you're burning out and you're pushing out these gases, right? So this is your force of action. Well, so what happens? That force of action causes a force of reaction. So the little particles, except that there's, billions and trillions, gazillions of them, that they're being pushed out, all of these are now causing in the opposite direction your force of reaction. So this is your force, okay, of reaction, which is now basically moving the rocket. Right now the rocket is huge, but if you burn enough, okay, then what you want to do, and if you want to be accelerating this rocket upwards, you have to overcome gravity. Right? So it has to be stronger than gravity, which is trying to bring you down. So that force reaction, so this force, so this will become your applied force, except on the rocket. And the same thing happens when the rocket is in space and it wants to start to accelerate. And if it wants to start to accelerate, what it will have to do, it's going to have to again burn off and hit off its engines so that the gases themselves start to come out. You have an action force, and then the gases will push back on the rocket, allowing it to accelerate. So I hope that these few examples now give you this concept and idea, and you can break it down, and this Newton's third law will make sense to you. So for every action, you have an equal, okay, it's simultaneously, okay, so it's at the same time as your action force, okay, and it is an opposite direction, a reaction force. All right, so thanks for watching. We'll see you in a future video. Bye, everybody.